same series. That's why I prefer it later, because if you study that material like you should and comprehend it, you probably aren't going to forget it before the final. That's my own opinion on it. I don't have any back it up. Okay, now I want to try to do this in a, when Nate finally gets done, or when we find out, Elijah, you email me the results if he gets it in this class or not. Because really, if it's a tie, we'll toss a coin. If not, then the majority rules, okay? And that would be, isn't that the date?
July 11th is so far what's winning.
All right, the 11th at 5?
Yes, sir. I'll take a photo of it to make sure, so there's no arguments.
Yeah. Actually, why don't you send this to me? And I forget it, Elijah. When we find out, then you send it to me. You would. Speaking of the devil,
I'm here. I'm here.
What do you want?
bring them up to speed.
So-
I have my interview in July, so probably June for me.
So,
Did everybody hear that?
where's the coin?
You got a coin?
My interview is kind of more important.
Yeah. Don't you have to go talk to the
I have to talk to the head admiral and then.
All right, all right, this is gonna settle it. Now, we're gonna do it this way. Heads, July 11th, tails, 23rd, ready?
Okay, so
Heads, the 11th.
head's going to be the eagle, tails is going to be the orange.
Elijah, you confirm this.
It's heads. What did you say?
Circle
Heads
the
was?
date.
You said July 11th is heads. I can look up that coin.
Circle it. This is the only way to do this, because I'm gonna tell you, in a class like this, if I set the date and somebody's mad about it, they're gonna send Dr. Nellens and toss it. Look, I try to do this as fair as possible. Nobody's gonna, but there's nothing I can do to please everybody usually. Okay? Now, I want to tell you one thing about this too, just for everybody's sake. I mean, I've told the other class, I have a grader this summer, and he's going to grade. His name is Yifan Zhang, and he's grading both classes. I just gave him the quizzes, and he'll get them done, and I'll get them back to you by Wednesday. Now, the solutions are up there. Do you see it? I want to tell you one thing. The original solutions had the wrong direction of propagation. They had X, I think. It is AZ, all right? And I think there was also the magnitude of eta, the intrinsic impedance, was off by a factor of 10 to the minus third. But now they're both correct, if you look on there. And it was meant to be a quiz that just made sure you understood what I covered in class. There was nothing supposed to be tricky. Alpha was equal to beta, so it's a good conductor. I told you it was going to be a good conductor. Alpha was equal to beta. After that, I think the only thing people messed up was getting the value of sigma right. And I mean, wavelength, 2 pi over beta, right? Wavelength, what else? Frequency, you just looked at the coefficient of t and divide by 2 pi. It was 10 to the third or fourth, something like that. Fifth, I'm not even sure. It was just an observational thing. For alpha, which is equal to beta for a good conductor, and if you look in there, I think you see it? Or you want me to put it up? If you want me to, I'll put it up. Since alpha equals beta and it's a good conductor, alpha is simply equal to the square root of pi f mu sigma. Do you all remember that? And since you got alpha, you got pi, you got f, you got mu. Square alpha divided by pi f mu, you got sigma. And it was meant to be, just check the boxes, make sure you understand it. But it's easy, especially if you're sleep deprived or cramming the night before, to confuse yourself. I promise you almost have this mode where I'm nervous, I didn't do enough, and you can make horrible mistakes. I hate to say that. Now, today, if there are no further questions about, I wish it would have been a unanimous decision for testing, but that's the only fair way I know to do it, is let the students do it. And you ran the thing, Colin, so I was even out of that meeting. So what I'm going to do now is talk to you. We just talked about propagation and good conduct, yes?
Could you go over on the homework?
Yeah,
question?
which one? Sure. I'd love to.
37. I will pull it up.
6.37?
Yes, sir.
Let me just take a quick look.
I believe it's the second one you.
All right, yeah,
gave us.
go ahead and give that to me. Now, let me tell you this. You're gonna see how a lot of stuff gets pulled together, especially when we talk about power flow. And I'll do that today, and we'll talk about polarization. He uses one statement, UP, or let's, university.
Not
university,
6.37, 6.38, sorry.
but he's gonna talk about a uniformly polarized wave. Now, I didn't talk about polarization, so let me step back for 1 second and do it. You're gonna see this is very easy. I wanna just give you a little idea when he talks about polarization, and I'm gonna start this way. Don't write anything, just listen. When you have a wave propagating towards that wall, if you think of waves on the ocean, they go like this. There's a vertical displacement. In other words, if you looked at the change in the height of the wave, it would have to do with the altitude or the height. You with me? With electromagnetic waves, they can propagate in a direction, and they can have a polarization or a vector sense in a unique direction. For instance, it could be vertical. And as they propagate, the magnitude of this, if you think about this as it was traveling, the wave crest, if you could somehow imagine that, would be going that way at a certain velocity of light, you might say, if it's free space. And the E field would be vertical if it's propagating that way, the H field would be this way, vertical and horizontal. Now, you can also have, at the same time, same frequency, same phase, an electric field that's this way, orthogonal to it. In other words, you could have an electric field in this direction and this direction. The net electric field will be some combination of the two. Y'all with me? This is when we talk about polarization, so let me get to it. If you have an electric field, let's just say it's propagating out of the board towards that wall, I'm gonna make it real simple. Call that, let's see, if I call this X, call that Y, X crossed Y is Z. So Z would be out of the paper. Just listen, you don't need to write anything. If you see this, I'll write the math for you, it's obvious. Now, if I have a wave that is simply an electric field in the Y direction, but it's traveling, you might say, out of the board, then you would look and see how it would change like this. By the same token, you could have an electric field at the same frequency of variation, an electric field in this direction. Let me get rid of that Z direction. It's confusing. It's kind of hard to appreciate what I'm saying with this. Just assume it's moving out of the board. So you can also have electric field, same phase in this direction, call it EX. The net summation of these two would be like this. This would be the total electric field. Now it is a combination of both a horizontal and a vertical electric field, but it's propagating in that direction. Do you follow me? Now if you looked at that for a second, and I'll try to be real clear about my next one, you can write this part down when I tell you to. If I just look at this, if this is X and this is Y, and I have an electric field like this, and the magnitude of that electric field never changes. I'm going to say it's just E naught. It's propagating that direction, okay? So if I have E, H would be orthogonal to that and would be 90 degrees. I'm trying to get different colors here to distinguish it, but I don't even know if I have a marker that's going to do this very well. If you think about that as E, H would be here. And there would be 90 degrees. Y'all with me? Now, here's what happens. Here's what can happen. If the magnitude of this never changes, but it's like the hands of a clock. If it rotated this way, say at this point, this is Z equals 0. Remember, it's propagating that way. If this tip of this thing rotated like that, it looks like the hands of a clock. The magnitude never changes. The only thing that changes, if we're at Z equals 0, if we let time increase, is it's rotating this way. Now, if the magnitude never changes, that's called circular polarization. And I'll tell you what to write in a second. It's because what this is doing, the tip of that electric field is carving out a circle. Can you all see that? A mathematical expression for that waveform. And don't worry about, there's different ways to do this. They'll have phasor and they'll have time limit. It really doesn't matter because I'm going to show you the trick. So the total E field, right, is going to be equal to some E, I'll call it EXAX plus some EYA1. You all with me? Now I'm going to write the mathematical expressions for these in a second. So I can say E itself would be equal to some, and I'll just call it E naught here. This is in the AX direction. And I can say it's cosine of omega t minus beta z AX. And then I can say it's plus, I'll call it E naught X right here, and I'll call it E naught Y. And cosine of omega t minus beta z right here. I'm going to tell you the different forms of polarization. What I'm just showing you here, it's called right-hand polarization, but I wanted to finish my thought on this. This is right-hand, it's called right-hand circular polarization. You'll get familiar with this. Now, here's how you know. First of all, it's circular because the magnitude never changes of the circle. It's carving out a circle. If it carved out an ellipse, it would be elliptical polarization. But they see how it says right? Now, here's the thing I want you to be attentive to. You got a right hand, I hope. Take your thumb on your right hand and put it in the direction of propagation. Now take your index finger and put it on the electric field vector. Increment time. If it's turning this way, like opening a door, it's right hand. If your left hand is in the direction of polarization, put your index finger there, and you're opening a door that way, or in other words, the tip is moving this way as you increment time, it would be called left hand. That should make sense. Your thumb always points in the direction of propagation. Now, let me explain something. These are the two types of circular. For elliptical, the only difference would be the magnitude, this is not circular, the magnitude of EX would be different than the magnitude of EY in terms of total size. You all with me? And as you add a phase angle, you can actually change the tilt or how the ellipse is structured. But there's one of the, and I'm sort of doing this in reverse order. If instead of a circle or ellipse, if it actually mapped this out, if this is X and this is Y, and the actual electric field vector simply made a straight line. In other words, the tip of the electric field would go like this. It would be an ellipse with no thickness. Think of it that way. You with me? That would be called linear polarization. The straight line is linear. You with me? I'm going to show you something. It's not hard to do this. So everybody gets concerned about, well, how can I tell what it is? And here's how you do it. No matter how they do it, they're going to give you an equation. It's either in the phasor or time domain. I'm going to stay in time because you know how to take a phasor and bring it to time. It's easier in time. And I want you to listen to this. So what I always do, and the easiest way to do this in my opinion, start by saying I'm going to plot what that vector does right there for the E field at different points in time or omega t, but I'm going to let z equal 0. I want you to notice this. When I make z equal 0, I don't want to go too fast. This is not hard though, I promise you. If I make z equal 0, I basically erase that. And I basically erase that. Do you all see that? I get rid of a variable. Now, omega t is an angle. Do you agree with that? Well, what you do is you start, and first you plot omega t equals 0. All right? Now, omega t equals 0. Well, what's the cosine of 0?
1.
It's 1. So I would have in the x direction E naught x, and in the y direction, this would be x. And this is really, I'm plotting the E field here, but I'm trying to give you, this would be EX, because it's in the x direction. It's a vector I'm trying to plot. And this would be EY, but the electric field here would have some, really, E naught Y, and some E naught X here. And if you actually combine these two, you get a point here. Can you all see this? Now, let omega t change. Let omega t, I'd increment it by 30 degrees, maybe 45 for this one, because it's pretty obvious. When omega t is 45 degrees, this is really 0.7070. Can you all see that? EX. And this is going to be 0.70, and I didn't put down the AY. I'm supposed to be a Y there. AY here. So it's really about 70% that, or this would be the first point. The second point would be right on that line, but less. Can you all see that? I want to make sure. How many see that? Now, keep incrementing it. Here's the next one. Can you see how it's going to just track out a straight line? That's linear polarization. In Whitwer's book, he talks about this. I don't care about what he's about to talk about, but he'll talk about, well, what's the tilt angle? What is this? And he'll say tilt angle. Now, how do you get the tilt angle? I'm going to give you a hint. Use basic trick. You know, first, you all agree that this thing's tracking back and forth, right? Tilt angle never changes that track. So if it never changes, what is it? Well, it's the opposite, where it's E naught Y over the adjacent E naught X, and that would be tau, the tilt angle. But you don't even have to worry about that. Now that is linear polarization because it tracks a straight line. You all see that? However, they can track a straight line in any direction. In other words, and I want you to just listen to this. I know you're writing this. I'm trying to gauge my lecture speed with the note takers. I mentioned that earlier, but I do that. I try to look, and if your head is enough, I'm trying to give you time. Now, what do you think if I wanted the thing to have only vertical polarization, what would I do? I make E naught X 0. Can you all see that? That would be an electric field in the Y direction, just moving up and down in magnitude. Can you see that? You see it, Nate? And if I wanted just horizontal, I get rid of the Y component. In other words, you can mathematically describe any type of polarization. You'll notice this one though, I have some arbitrary magnitude here, and I got the argument cosine omega t. Now, for elliptical polarization, I can simply, matter of fact, what I'm going to do is this. Next one I'm going to show you circular. But I'll show you how easy it is to figure out if it's right hand or left hand, because that's always what people are worried about. I'm going to make both of these the same magnitude, so I'm just going to call them E0. I hope I don't cause you too much trouble, but I want you to see this. Remember, the first was linear. I didn't spend much time because it's pretty obvious. Now, for circular polarization, there's one thing that'll happen. There'll always be a phase angle in here of pi over 2. 90-degree phase difference between one field component and the other, but the magnitude is the same. Does that make sense to everybody? Let me just show you. I'm going to put the phase component here, plus, and I don't like to use degrees. Normally it's pi over 2. But I'll put 90 degrees just so it's clear. It should be pi over 2 for units of degree. You with me? Now just listen to me. So how would you figure out if it's right-hand circular polarization? I'm going to plot right here. I think you guys have seen this. If this is EX and this is EY, first you start out and you let omega t just as before equals 0. When omega t equals 0, now listen, now you plot this point. When omega t equals 0, I got cosine of 90 degrees, which is 0, right? I got 0 in the x direction, and I got 1, or I have E naught and a Y. So the first point would be here. Now you put like a hands of a clock. This would be point 1, and it would have a magnitude of E naught, right? Now let omega t increment by, say, 45 degrees. So now I have cosine of 45 degrees in wider. What is that? 1 over square root 2 of 0.707, right? 70% of the original times E naught, whatever E naught is. So now I mark out a little point here, 0.707 E naught right there. What about the x component? This will tell you which way it's going. When omega t is equal to 45 degrees, that's 135. Think about a cosine waveform. If this is theta and this is cosine of theta, and this is 0, well, it does this. Here's 90, and then it starts going negative. Can everybody see that? So it would be minus 1 over square root 2 times E naught. Can you all see that? Can you follow me? I gotta make sure you see this. So where is that? It's over here. It started here. Now for this second point right here, it coincides with a point here. And this means that this is the way the hands, they still have a magnitude of 1. The hands of the clock are turning. Can you all see that right there? What polarization is that?
Right hand.
Right hand, circular polarization. Does that make sense? Take your right hand out. Remember, it's moving that way. That's plus Z. Y'all see it? Follow me? Now, next, if you got that, what if I wanted it left hand? Anybody want to take a guess? There's no wrong answers. That's it. Just making mine is not amazing. Now there are millions of ways. Probably, I don't know how many. There are a lot of different ways to do it. I could have a minus sign in front of E naught. I can do all sorts of rotten, no good things, but I'm not gonna. Instead of cosine, I could have a sine. Follow me? All sorts of dirty tricks. I don't do that, but I'm going to tell you, no matter what dirty tricks play, you increment the omega t. Let z equal 0, increment omega t, and just plot the points at the tip of the vector for each one of those different values of omega t and see which way it's moving. Take a guess that if I wanted to make it elliptical, there's a lot of ways to do this too. I'm going to put back the plus, by the way. If I wanted elliptical polarization, what would be one way of getting it? Anybody?
Making the AY direction value different.
Yeah, how about make it 2, right? 2, yeah, now that's an egg, it's an ellipse. And it's laying on its side, you might, well, it would be laying, the egg would be oriented with long axis up, major axis up, right? What if you wanted to add a little tilt to it? Add some angles here. But always just plot points. That's the way you do this all the time. You with me on this? Now, don't worry about Whitmer's book. He has all these little tricks. Well, you put it in the phasor lane. If this has such and such, it's a waste of time. This is how you do it. And by the way, the only thing you really care about in the real world, is it linear polarization or is it elliptical / circular? And here's why. I'm going to give you a tip. I'm going to just tell you, like, the bottom line, why it's so important. And you'll see this. We did reflection from surfaces, right? I want to talk more about that in a second, but I just want you to understand this because I'm going to get to your question. I just want to make sure it's clear. If I have a radar here and it can send out a circularly polarized wave, we'll get to how that can happen later with antennas. And I'm sending it that way. And there's something out there that reflects. For the sake of Nate here, we'll talk about a ship. So let's assume there's a ship at sea, and this is, you may know this one, SPS 49 or 48 radars on the carrier. You know this one? These are old World War II radars, but they're still used, and I'm very familiar, not very, but I'm familiar with both because I've had to deal with both. And I send out a signal. This is a long-range navigational radar. I think the 3D radar circuit, but not the navigation.
I can't tell you about the radars, I just know they're there.
Yeah, they've been there a long time, since just after Pearl Harbor. Anyway, basically it goes on, it's a right-hand circularly polarized wave. Follow me? If it hits a conducting target, a ship, it reflects back left hand. With me? Now there's polarization filters. I can figure that out. So now I know I sent a waveform at a given frequency that's right-handed. If I get a wave back and it's left-hand polarization, I'm pretty sure it's what I sent, which means I know the total time it took, it's called time of flight, because it's moving at the speed of light, goes out, hits, comes back. Hey, that's what I sent. Guess what? I simply I know that the distance it travels is 2r, right? I know that is c times the total time of flight. So I put c, total time of flight, which I can figure out. It's like an echo. You yell and listen. How long did it take for the thing to come back, the echo? So I know total time of flight, and I know it's mine, you might say, because now it's left-hand polarization. If I want the distance, well, that's 2r, because it went out to the target and back. So I take c times the time delay divided by 2, and I got the distance to the target. That's how you get ranging information the most simple way. But that's why it's so important to know if it's right-hand or left-hand polarization that you get back. And the reason is, in this day and age, there's so many signals out there. And remember, with radar, the signal you get back is such a small fraction of the strength of the signal you sent. You got to use every possible way of discerning or discrimination, knowing it's your signal. There's other tricks too. But that's why this stuff with polarization is so important. Another thing, and I'm not an expert in this, you ever seen the weather radars? You know what I'm talking about? You'll see them and they'll have color code for, like, dark red is a lot of rain and stuff like this. One thing they'll do too, they'll have something called Doppler radar. Have you heard of this? I'm going way down, I'll talk about this later. Doppler radar gives you a velocity that we'll see. But they have another thing where they can get basically kind of, if they're looking at rain, it's falling this way. Raindrops are like, they're teardrop shaped. They have a long axis and a short axis. Well, if you can polarize a wave, so it's elliptical, and the axis is basically going to coincide with how this rain's falling, the tilt angle on that, you get the maximum return. So there's another way with, and I'm not an expert, so this is way beyond what I feel comfortable talking about, but I'm just going to tell you. They can use all this stuff. They send out a right, it comes back a left, it's my signal. The maximum amount of signal strength I get from that is when I'm polarized with elliptical polarization like this, I get the maximum return. Now I'm pretty sure I know the direction of the rain is falling, the approximate density because of the strength of the return, and I can get all sorts of information. Now that's the key to why all this is important. It's not just abstract. It's very valuable for a lot of stuff in the future. Anyway, that's polarization. Now, getting back to your problem, or I should say your problem, what I want to tell you is what I put down there was something where you had to read about this, because he talks about and it'll be a uniformly polarized wave, or what does he call it, UP?
Yeah. So I'm gonna be honest, we can still do this, but my question was on 6.3a.
We'll do it.
Sorry,
That's all right. I had to cover that anyway today. I might as well get it out of my system.
Fair enough. Yeah, but UPW, just an acronym. He says a UPW is a normally incident from
Uniformly polarized wave. Go ahead.
Is Z is less than 0, sigma equals 0.
All right, hold it. Z less than 0?
Yes, sir.
All right, so they got some kind of region. I'll put this as Z in this direction. And this is going to be Z less than 0. I'll call it this. Go ahead.
With sigma equals 0, mu relative is 1, epsilon relative is 4, and then for media 2, Z is greater than 0.
Well, this is 4?
Yes, sir. Epsilon relative is 4.
Oh, this is rotten. Okay, he's doing it the reverse. So now what is sigma 0?
Sigma is still 0, with mu relative now being 8, and epsilon relative being 2.
Okay, so he's got different, it's a lossless region if you look at this. Sigma is 0, so it's lossless. Everybody follow me? Now what does he want to know?
Calculate reflection transmission coefficients.
Which way is the wave coming from? Region 1 or region 2? He's assuming it's moving the positive Z direction. He doesn't say that, I don't.
Assuming right, because 1 to 2 and Z is less than 0,
Yeah,
so.
he doesn't say, he doesn't give you an equation. What he's assuming is the wave is going that way. That's what he's assuming. So This is region 1, this is region 2. And he wants reflection coefficient?
In transmission, yes, sir.
Well, okay, let's, first, to do this, we need eta in this region. I'll call it eta 1. That's the square root of j omega mu over sigma plus j omega epsilon. I'm writing the full equation. Do you agree with that? You need to know that base. Do you know what I'm writing here? Do you follow me? This is the intrinsic impedance of the region, the square root of j omega mu over sigma plus j omega epsilon. I wrote that for a reason this way. I know sigma is 0, but I want to make sure this is the entirety. This is eta, correct? What, right? How many know that? All right, now let's get rid of sigma because there's 0. This is in region 1, right? What do you notice happening with the j omegas?
Cancel.
0, yeah. That means eta in region 1 is really equal to the square root of mu naught over epsilon naught times the square root of mu relative in region 1 over epsilon relative in region 1. I did that for a reason. You all with me on this? With me? Why do you think I put that, and I think all of you know, square root of mu naught over epsilon naught? 120 pi. Very, very good. 120 pi, that's used all the time, and it's times this square root. Mu relative 1 over mu, or over epsilon relative 1. Now I'm going to show you something in a second. Let's go over here. And that means in region 1, the intrinsic impedance is really equal to eta naught times the square root of mu relative 1 over epsilon relative 1 over, or really over 2. Do you agree with that first? I'm going to let you guys catch up. Are you with me on this, everyone? Okay. What about region 2? What is it? You can, because sigma is 0, you can go right here and just substitute the region 2 parameters. Go ahead.
It would just be 2 times 2 is not.
It's going to be what? Eta naught. You're right. 8, I think. Eta naught, right? And then square root of what? 8 over 2, or square root of 4 is 2, right? Now, what is the reflection coefficient if we assume the wave is traveling from z minus to z plus?
It would be eta 2 minus eta 1 over eta 2 plus eta 1.
You know, what I always do is say it's the intrinsic impedance you're going into minus the intrinsic impedance you came from, over eta 2 over the sum of the two of them. What I'm really trying to do is kind of get you thinking the way I think about this is always the impedance you're going into minus the impedance you came from, intrinsic, over the sum of the two. Well, what's that going to be? Well, the reason I put down that eta naught in there is because they're going to cancel top and bottom. So it'll save you time with your calculations. Everybody with me? So here, for the first one, I go into region 2, so it's going to be 2. Eta naught's going to cancel. It's minus eta 1, or minus 1/2, over 2 plus 1/2. So that's really going to be, if I look at this, I got 4 halves minus 1/2 is 3 halves, and this is going to be 4 halves plus 1/2 is 5 halves, or this should be 3/5 for reflection coefficient. Now what about the transmission coefficient?
1 minus.
What you know is what? Transmission coefficient is 1 plus reflection coefficient. Do you remember that? We can do it 2 ways. So you tell me if I'm right. It's 1 plus reflection coefficient, region 1. So it's going to be 3/5 plus 5/5 or 8/5. Does he have that?
He has it in decimal, but yeah, 1.6. So.
You all with me? Now, something I'm going to ask too. Well, I better just stop here. That's how you do that problem. I know I spent some time on polarization, but I have to cover that, and I figured this is as good as time as any because he talks about uniformly polarized waves. This is what he means. It's just a wave where nothing varies in terms of the frequency or anything. It could be circular, it could be elliptical, it could be linear, but it's the term. What else in that one? Anything else?
No, sir. You can move on.
How many did these problems? Just be honest. All right. I suggest you make sure you cover these problems, do them, and if you have any questions, come to me. Don't get behind us, because this is where you can really get yourself confused. Anyway, so that's polarization, and that is really just some basic information about reflection and transmission. I think that we should do just one more thing with this before we get into power. Well, I'm going to tell you, I'll do this in a second. Next one, what I'm about to tell you, this takes a little time to set up. But there's a thing in section 6.8 about reflection and transmission from oblique incidence. Do you see that? This is section 6.8, but I got to tell you what I mean by that. So suppose I have a wave. I'm going to use this wall as an example. If I have a wave and it's going propagating right into that wall, say the electric field is this way, and it hits it, it bounces back. That's called normal incidence. It means the wave's vector direction is going to be perpendicular to the plane of the wall. But there's something called oblique incidence, and it means this. If the wave is propagating in this direction, doesn't matter which way the electric field is oriented, and it hits this, it isn't coming in normal, it's at an angle. Can you all see that? That is called oblique incidence. And when you have oblique incidence, you can have two types of electric fields. I'm not going to do it right now, I'm just getting your mind ready. You can have an electric field that is polarized this way. In other words, the electric field, when it hit, like if it's normal incidence, the whole electric field is tangent to the region, the separating region. I mean, the barrier that separates it. Can you see it over there? But if it's coming in like this, if the wave is moving this way and it hits, the component of the electric field that is parallel to it is not the length of that, but the H field is parallel to it. Now that's called, what he's going to call this is, and you don't need to write this down right now, I'm going to go, that's called parallel polarization. And here's what, maybe I shouldn't have said it better there. Now there's another thing that can happen. If the electric field is in a direction, say towards that wall, right towards that wall, parallel, and the electric field is propagating like this and hits, the old electric field is tangent to the wall, all right? And that's called perpendicular polarization. Now I gotta tell you this. I don't want you to worry about the definitions. I'll take you through it when time allows. But this is something that is going to be coming in the future, and it gets complicated. Before I do that, I need to do a few other things so that you won't go crazy. If you start reading 6.8 now, you're going to look at me like, how dare you? And I'd feel really bad, but I have to set this up. The reason we're going to do some of the other stuff is so you get an understanding and appreciation for why we're going to do that. I mean, you may not see it yet, but you will. Okay. I did the polarization. Next thing I'm going to talk about, we did conductors, dielectrics. By the way, a lot of you probably wonder, well, you're going to give me a problem with epsilon double prime or epsilon complex in there for a quiz or for a test? No, probably not. If I'm going to do it, believe me, you will know there'll be all sorts of stuff. I'll put circles around and everything like that. The reason I'm telling you about that is in the real world you need to have an appreciation for that, because you'll be experiencing your boss or somebody you're working with talking about that, and you have to be exposed to it. That's the reason I say these things. But I'm going to talk about pointing vectors. This is section 6.5, and this really has to do with power flow. And I'll show you how it applies to. There it is. I didn't check the weather, but is it supposed to rain?
Not today, but the rest of the week doesn't look all that pretty.
I want to tell you about what we're going to cover. It is exactly, it's so similar to real power flow or average power flow in electric circuits. And I don't want, you can go nuts looking at the final details of this, but you don't need to. So this is called really the pointing vector theorem. That's a P, by the way. Pointing vector. And Whitmer's book is gonna talk about power flow. And it's analogous to average power flow when you're talking about circuits. Okay, so what is it? Well, if you have an electric field that's got some Z and T, right? You're gonna also have a magnetic field caused by this. These are gonna be propagating plane waves. The entire chapter 6 only deals with plane wave propagation. So it never has to do with what are called near fields that I'll get into and things. These are propagations, waves. You're a long way from the source. They're basically a plane wave. And you have an H field of Z and T. And both of these are related. The E field will, if it's polarized in a certain direction, this is 90 degrees difference. Same frequency, and one gives rise to the other. You can't have the E field without the H field and vice versa. So if you have these, don't worry about anything else. There's a thing called the instantaneous pointing vector. And the symbol really is this. It's a vector. And what it is simply the E field, the vector E field, and it's a cross product operator into the H field. That's all it is. It's going to be a vector direction. No big deal. But what it really does is tell you something. It will give you the power flow, and it will be in watts per meter squared. Now, you remember, I want you to recall this. When we were talking about power flow, and it was at a constant frequency, right? There's one thing you noticed, and I'm gonna just tell you this. We know that voltage and current may have this type of relationship. That could be voltage, this could be the current, and if you multiply them, I'm going to just show you this. Now, you don't need to write this. I'm showing this so you appreciate what I'm talking about. If this is actually some time, and this is going to be the voltage, current, voltage, V of t, and it's really times I of t. That is called the power, and it's instantaneous, and it would do something like this. Basically, it would never go, this thing, well, I said it could go negative, but it basically, if you're talking about P of t, actually, let's assume it's real. It's basically going to do this. You're going to have something where the frequency that V of t is oscillating will be doubled for the power. For instance, if you have a 60 hertz outlet, right? You have a waveform, a voltage waveform that's varying at 60 hertz, right? 60 times a second. You got a current variance, but the actual power flow, because it's voltage times current, when you multiply the two together, what you're going to find is the power varies at 120 hertz. The flicker on those lights is not 60, it's 120 hertz. Do you know this, class? How many know what I'm talking about here? That's instantaneous, and for instantaneous stuff, we don't spend that much time on it because anytime you have a steady or a constant frequency of excitation like a cosine of omega t variation, we worry about average power. You all remember that from circuits? You worried about average power? Did you have the power course yet or not? How many have had the power course? You remember that they talk about RMS current, RMS voltage? The reason they do is because RMS voltage, RMS current is average power if you multiply them, right? If you take the cosine of the angle between them, or power factor. Well, what we usually do in electromagnetics almost always, we worry about the average power flow here. So here's what happens. Most of the time I'm not that wordy, but I think it'll help you guys get appreciation for this. So if we have an electric field and we have a propagating electric field that's planar, now we talk about average power flow. it's really power density. And that is this, P ab will be equal to, it's a vector, is going to be 1/2, and then it's the real part of E, that's a vector, but these will be in the phasor domain. It's going to be the vector E crossed in to the vector H, but it's conjugated. I didn't put this down, but you remember when you actually had average power flow, and you're talking about circuits and stuff, it was 1/2 the real part of V times I conjugated. Do you all remember that? The conjugation got rid of the frequency, to be frank about it. There is no J omega T in the average power flow. There's only something called a power factor. It's the cosine of the phase difference between the voltage and the current. That's what this means, conjugation. But the units of this, of P ab, whatever this comes down to, I will put it 1/2 the real part of E cross H conjugate. These are phasor form. The units are watts per meter squared. That's important to remember. Power is watts, right? Volts times current is watts. Now it's going to be power flowing per meter squared, and it will be in the direction of propagation always. That's an important fact. Let me get to the next part, because really, you need to see this applied. You got an idea about what this is? Let's see it applied. That way you'll get a feel for it. And by the way, the section on pointing vector, P-O-Y-N-T-I-N-G, is on page 342 of section 6.5. And he gives an example I wasn't worried about. Then write this down, formula 6.84 is the one you want to look at. And now we're going to do it in phasor domain. I'm going to show you typical stuff we do. Why is this important to me? And do some calculations with it. Who had a test today? Didn't some of you guys, you had a test today, Elijah? And you? Okay. Well, I can imagine you probably are not immersed deeply in the homework, but.
Yeah.
Huh?
Test one by bad.
Was it econ?
Engineering econ.
I don't even know what they asked you in there, but.
It's like business flow stuff.
Time value of
money.
Compound interest
Yeah.
rates.
Yeah.
So, well, engineers, it's probably a joke to you guys. Anytime, see, that isn't bad stuff like this. Whenever they have something for laws and how law applies to business, because there's a ton of laws you gotta know. If you're, anybody here take business law? If you ever get a chance to take business law, I would take it. It makes you know what you're liable for. Because when you sign your name, and especially if you have a professional engineering license, you all of a sudden become liable for anything that doesn't work the way you say it does. And if anybody injures himself, you can be, unless you have insurance, you can shell out millions of dollars. Be careful about that. Okay, so when we have this, we're going to use power. Average power is the one we care about. So average power, and it's power density, but I'm using this symbol. It's going to be 1/2 the real part of E cross H conjugate. Right? So let's write the equations, the basic total equation. When we have an electric field propagating in free space, I have to make some assumptions. I'm going to assume it's going in the z direction, and I'm going to assume that the electric field is it's going to be a plane wave, And it's going in the z direction, polarized in the x. So, and this is what I'm gonna call it E naught. Now because I'll allow for loss, I'll put in e to the minus alpha z and e to the minus j beta z here. And then I've got to give it a polarization, so I'm going to say this is the AX direction. Do you remember that general form for an electric field? Propagating in the positive z direction. With me? Now, there's going to be an associated H field we can get. Normally, if we didn't know what we're doing, we'd say it's 1 over eta, right? But eta can be complex, so I'm going to put 1 over magnitude of eta. And then I'll take the phase angle and bring it upstairs. I'll put it right here for now. So it's going to be e to the minus j, the angle associated with eta. Y'all follow me on this? Because 1 over the magnitude, and then I would have to take e to the j eta here, but I don't want it downstairs, I bring it upstairs on top, on the numerator. With me? And it would be a unit vector in the direction of propagation. In this case, it's az, right? Then it's crossed into the E field, or crossed into E naught, e to the minus alpha z, e to the minus j beta z, and the direction in this case would be ay. I'm not going to prove all that, but I think you all know that, right? I mean, so after the cross product is done, it's going to be ay. I'm not even going to bother going through that. The reason is I'm trying to just get to the essence. And I'm going to rearrange this a little. I'm going to take this phase and put it in with that beta. So this whole thing will become equal to E naught over magnitude of beta, e to the minus alpha z, and it's going to be e to the minus j quantity beta z plus the phase angle associated with the intrinsic impedance a. Why? I want you to just take a look at that. Remember doing this class? We can go through the cross product, the 1 over eta, direction of propagation, a sub p, and crossed into e, but this is what it's going to be. Y'all follow me? Now take a moment. I do envy you people with those pads, because that looks very, I would hate to work there on that. You know what? Look at how much board space I used just there. I'd be using so much of that, I wouldn't be able to get it all down on one sheet. I think it went this big. Anyway, with me? I mean, how many remember doing this? Okay. You don't? If you don't remember doing it, become very familiar with it, because we're going to use this all the time. So now we're going to get the power flow associated with that. I think you'll see this. I'm giving you the general format, and we'll show you what happens for specific cases in a second. So now the average power flow for this, P-ab, is 1/2, make sure you get that 1/2 too, the real part of E crossed H conjugated. Just stating what the definition is. Now I'll put the values in. So P-ab will be 1/2 the real part of the E field. I'm going to write the E field in here, which is just E naught e to the minus alpha z e to the minus j beta z, and it's in the AX direction. This is going to be crossed. I'm going to circle that cross product so you can see it doesn't mean the symbol X is as an indice of measure, something having to do with a measure of distance X. It's just a cross product. And then it's crossed into the H field. H field has a magnitude of E naught over magnitude of beta times e to the minus alpha z, but then it's times e to the minus j beta z plus the phase angle associated with eta, and this is going to be in the AY direction. But there's one thing, and I want your attention, so I'll let you write that down. I haven't done yet. What does conjugation mean? this is the equation for the H field, but I didn't conjugate. What do I have to do? What?
180.
What you're talking about is right, but in essence, see that angle? Whatever is multiplying e to the j, whatever, you make it the opposite, e to the minus, it's e to the minus j, so it becomes e to the plus j, all right? And what does that do for us? Here's what happens. I want you to follow me. When I break out, and this is in his book, I'll tell you the equation, so if you can't read my writing, you'll have it in front of you. Hopefully he has this.
6.86?
No, it's 6.87. Write down 6.87. Equation 6.87 on 346. I'm going to write it down, but I'll show you what happens. Just for one time, you have to see this. If you look at this, the 1/2 stays, right? Now, real part, everything that's real you can put out in front. You see how I have E naught times E naught? That's E naught squared. So out in front, I'm going to have 1/2, and I'm going to have E naught, the magnitude, squared, and I have, divide that by magnitude of eta. Now, it's important to note that. But what happens when I have e to the minus j beta z times e to the plus j beta z? They go to 1. Do y'all see that? E to the a times e to the minus a is 1. Do y'all follow me? So that goes away. That term and that term I x. Then I have e to the minus alpha z times e to the minus alpha z, both real. So it's going to be e to the minus 2 alpha z. And then finally, I'm left, if you just look at this for a second, I've taken out everything and accounted for it, got rid of the beta z, but you see how there's an e to the j theta, the angle associated with the impedance right here? I need the real part of that. What's the real part of e to the j theta? Cosine, right? It's just times cosine of theta of that angle. And it will be flowing, ax cross ay is? AZ, it's the direction of propagation. Can you all see that? Now that's it in a nutshell, what's going on. Really, it is. There's something you can see. All these right here are constants in a given region. Do you see that? So you can say that this really is some P0. And that P0 right there is just equal to 1/2 E naught squared over the magnitude of eta. That's all it is. And it's times E to the minus 2 alpha z. Now that means it's going down at twice the rate of the electric field or the magnetic field. You all follow me? E to the minus 2 alpha z. Is everybody with me on why it's that? And then you got that, you're going to have this thing. Now it's going to be cosine of that angle. In fact, I'm going to take that cosine of that angle and multiply P0 by it, because that's a constant. Do you agree with that? Matter of fact, I'm doing it this way only to bring your attention to the fact that if you have a loss in material, you have to make sure that you multiply the power, the 1/2 magnitude of E naught squared over eta, by the cosine, because it will be reduced, because there's a phase angle difference between the two. And it will be in the AZ direction. The units are watts per meter squared. Now, honestly, that kind of tells the tale right there. That really does. And he gives some example problems. I don't think you'll have trouble with it, but I'm going to show you a couple other things that I would, I think are important. So all this is going to apply now to a problem with it, where I'm going to take effectively I'm going to make what's called a shield. And I want to tell you, this is in a later chapter. I think it's chapter 9. But don't worry, it fits perfectly here, because You just covered reflection and transmission from different interfaces, right, or different materials. I should say different regions of space with different material properties. Now we're going to talk about something that's all this applies to, and it's very important. It's called a shield. You've heard of shields before, right? So somebody tell me what a shield does. Anyone? You're in the military. What does a shield do?
What type of shield?
How about,
A shield can reduce how much, I don't know.
he's onto it. It protects. It
Yeah.
reduces something you don't want to hit
Yeah.
you, right? A shield stops bullets if it's a bullet shield. I mean, basically, a shield is something that's going to eliminate something you don't want. That's it in a nutshell. That's all it means. The term actually is ancient. It didn't have anything to do with electromagnetics. It had to do with rocks and stones and swords. When I have people. Am I wrong that what?
Basic class is over at 2:15.
Isn't it 2:30?
2:30.
You told me 2:15.
You guys, I said 2:15?
Yes, you did.
All right, Grayson,
I'll see you in your office in 15.
you can sue me.
What?
I probably did. He's a very bright guy. He's also trouble. Comes down here to let me know. You're not in your office. All right, here's the problem in a nutshell. We're gonna have a material here. I gotta start by drawing it. And this is a good one, so. We're gonna call this air because that's what we usually apply these things to. Means eta is just equal to eta naught. This is region 1, all right? Now, we're gonna have a region here. And this is gonna be 0, and this is the z-axis. And this thing's gonna have a certain thickness. I'm just gonna use the symbol T for thickness. It doesn't matter. I know you can think, well, it means time. No, just any unit, any symbol you want to show the thickness of the shield. This is the shield right here. And you might say that it's typically made of metal, because it's true, but this is trying to give you perspective on what's really going on. This material is, and then it's going to be air out here. So I got air, material, shield, air. With me? I want you to pay attention to this. This material is going to have some epsilon relative, mu relative, and sigma. And this is for the material right here, not for air. I'm trying to distinguish this. All this has to do with this material. Maybe I'll put it here. It's going to have epsilon relative, mu relative, and sigma. And that means this material is going to have a unique value for eta, and call it eta of the shield. All right? Have a magnitude of eta shield, and it'll be at an angle. With me? There's also going to be something about this that's unique, this shield. It's going to have gamma equal to alpha plus j beta. Almost always shields are very good conductors. Almost always. There's exceptions, and they have to do when weight's an issue. Then they'll use some form of a dielectric shield, because for, like, if you want to shoot something into space, every little ounce is a lot of money you're wasting with rocket fuel. So they want shields that go into space, or they want them as light as possible, and that means sometimes not good conductors to be used for shields. But in general, alpha is beta, and in general, gamma, and this is of the shield, is equal to square root of j omega mu times sigma plus j omega epsilon. You with me? Now I want you to understand what happens. So I just tell you, those are the parameters. And now we assume we have a wave propagating into the shield. I'll just call it an incident electric field. I call this the x direction. So I have that. It's propagating this way. With me? Now some of this waveform is going to be reflected this way. You all see that? That would be the reflected field. And some of it will be transmitted. Or there'll be a component of the electric field transmitted. First, does that make sense to everybody? I'm just showing you, basically you're going to have an electric field incident, electric field reflected, electric field transmitted. I'm going to try to draw this without so much clutter. This is the z direction. This is the thickness T. I have an incident electric field as such propagating this way. This is air. It hits. I'm going to have a reflected field propagating that way. And I'm going to have a transmitted field propagating this way. Do y'all follow me? Now, I'm going to assume one other thing. I'm going to assume the thickness is greater. Actually, let's put, greater than the skin depth in this material. Skin depth in shield. So now, if you look at this, I need the reflection coefficient right here, and I need the transmission coefficient, right? Do y'all follow me? Call this the first transmission coefficient, and this the first reflection. Call this boundary 1, and call this boundary 2. With me? Just get a feel for so I want the reflection coefficient. It means I need the intrinsic impedance in region 1, which just is eta naught. The intrinsic impedance in the shield, right? And then I can get it. What I'm really after is the transmission coefficient, but we'll do them all. Reflection coefficient in region 1 is eta shield minus eta naught over eta shield plus eta naught. You all agree with that? Now, transmission coefficient region 1, you can say it's 1 plus reflection coefficient region 1, or you can write, like I do a lot of times, 2. And the reason I'm saying that is because this can be so close to -1 sometimes that 1 minus 1, if you just round it, is 0, seems like. But this is a better way to do it. Just take 2 times eta shield over eta shield plus eta naught. I do that for a reason. That eta shield is going to have a value. It may be small, but it's not going to be 0. You with me? That's the transmission coefficient. So now I want the electric field that's transmitted just on this side of the shield. You with me? So here's a shield. Well, the electric field transmitted just there will be the transmission coefficient times the magnitude of the incident electric field. Are you with me, class? Y'all follow me? So I can say the electric field transmitted, and I'll call it ET0, is just going to be transmission coefficient in region 1 times E naught incident. Can everybody follow me on this? I'm just showing you literally, that's the electric field just past the boundary between air and the shield, right? But that shield, that electric field is going to now start falling off in magnitude and change in phase, but it will be related to the parameters in the shield, not in free space. So I can actually say that the electric field in the shield itself, that's propagating in the positive direction, at least at this point, would be equal to E naught transmitted, and then it would be times E to the minus alpha, and that would be in the shield times Z, I'll get out of your way, times E to the minus J beta in the shield times Z. And I'm going to say it's in the AX direction. Do you all follow me on that, class? This right here is really just, I could put E naught incident times transmission coefficient right here for all intents and purposes. Do you agree with that? Now, it's falling off, or it's decaying at E to the minus alpha Z. You all with me? Here's what, when we start talking about shield stuff, let me just finish this thought, right? you always worry about the magnitude of the electric field, not the phase. That phase term you can forget about. So I'm gonna say the magnitude of the electric field in the shield as a function of Z will be equal to, just go ahead and put this in. I'm gonna say it's tau 1 E naught right there, incident. And then it's gonna be e to the minus alpha Z. And that's how it would decay. Can everybody follow me on this? It's basically, if you were to take a look at a map of the magnitude, it would basically be doing this. If this is the value E naught transmitted right here, it's decaying down to some point right here. Y'all follow me? How many do right here? What happens is the magnitude's decaying. At this point, it may only be 1,000, 130,000, 1 millionth the value here. Y'all, it's decaying rapidly. So now I want to get the value of the electric field right here. That's just before it leaves. And I can say now this is going to be E in the shield magnitude. Here, Z is going to be equal to the thickness of the shield. I'll get out of your way. And I said that's equal to this, tau 1, E naught incident. You can take a magnitude of that if you want. And now it's going to be E to the minus alpha times thickness of the shield. Do you all see that, class? Because now Z becomes the thickness of the shield, right? We're not quite done yet. We want to find the electric field value as right out here in air. I want to find E naught transmitted. How much gets out? Now I want you to listen carefully. This is the transmission coefficient between this region and this region. Now pay attention. Are you with me? I gotta wait until everybody's done writing and I will make my point. And thank you for staying with me for a minute or two over right now. I want to just finish this thought. So the transmission coefficient here, and I want to call it tau 2. It's the impedance you're going into, this is air, it doesn't say air, but it should be air. So it's going to be 2, but remember, it's going to be an impedance you're going into, which is, the transmission, this would be the reflection coefficient. Transmission coefficient is what? Twice the impedance you're going in. You could calculate reflection, reflection coefficient, add 1 to it, but I want to show you the trick. Well, actually, it's going to be 2 times the impedance you're going into, eta naught, over the impedance you're going into plus the impedance you came from. You all see that? Now I'm going to show you the real trick on this. I want you to be attentive. Remember last quiz? The intrinsic impedance was like 10 to the minus third times something, wasn't it? It was milliohms. Do you remember that class? The last class, quiz 2. It was so far into the noise, like who cares, right? But, well, it's important to actually get that right. Compared to 120 pi, which is about 377, 377 plus 10 to the minus third anything is about 377. Do you agree with this? This is about 2, almost always for shields, just about 2, which means the transmitted electric field, at the end of the day, write this down, is going to be, when I take this and multiply it by 2, because that's the value just on that side, now it wants to get out. So it's going to be 2 times the magnitude of tau 1, right there. Then it's going to be times magnitude of E naught incident times E to the minus alpha t. That's the transmitted field. I'm going to finish up right here. So we're assuming the shield's thick enough so this doesn't happen. You got some here, goes in, hits, and then reflects back, hits here, then reflects this way, hits, and gets through again, where you have a multi-bounce problem where you got to worry about every single reflection. That will happen with shields not made with good conductors, light shields. You have to worry about the multi-bounce stuff, but that's later. Now follow me on this. If this is the case, the last thing, this is called the shielding effectiveness. or SE, and it is this. It's equal to 20 times the log, it's a base 10 log, of the magnitude of the incident electric field over the transmitted electric field. And I'm gonna finish my thought. I'm gonna show you, where's that? Okay, that's there. Let me just write the final form of that. This is called shielding effectiveness. It is in dB. And it is the way we actually attach a figure of merit to the shield's, you might say, goodness, or how well it shields. So the shielding effectiveness is equal to 20 times the log of the magnitude. The incident electric field is E naught incident divided by the transmit. You'll notice that the E naught incident is going to cancel, so I'll just put it out here and cancel it. Then it's times tau 1 times 2 times e to the minus alpha times thickness. Or I can just say shielding effectiveness is equal to 20 times the log of the magnitude of, and you might as well just do it this way, 1 over, you can take magnitude of tau 1 and take magnitude of tau 2, say it's not 2, but it's going to be about 2 anyway, and then it's times, you can take this upstairs and make it e to the plus alpha times the thickness, and that'll work every time. Y'all with me? I'll give you homework on this, and I hope you, I didn't mean to keep you this long, but I wanted to finish that thought before I broke loose. I'll cover more of this on Wednesday. I'm going to give you homework on this stuff. And the last thing we'll do, if I have time on Wednesday, will be oblique incidents. Oblique may seem a little taxing, kind of drive you nuts, but I'm going to level with you. I'll tell you the stuff you need to be aware of with oblique incidents and just cut to the chase. I don't expect you to be able to mathematically recreate